Okay, hey honors physics, it's Miss Haynes again. Sorry that I don't have somebody to tape me right now and I'm just using my phone. But today we're going to do 17.4 and it is electric power, and it's really not that hard. It is probably the last, no, this is the last section in this unit, and so right after this you have a quiz, you have another lab that's due on the 1st, and then you have a unit test. So here are my notes, which I have downloaded to the assignment for this section. So when we're talking about electric power, we are talking about how do the electrons generate from chemical energy or some other type of energy, whether it's kinetic and flow throughout. So basically, free electrons will move from positions of high electric potential energy to lower electric potential, and this maintains the current. So current flow is going from high to low. So we have batteries, which are chemical potential energy. So it has some kind of chemical stored inside of it, and it converts chemical potential energy to electric. So food can be a type of chemical potential energy because food is basically energy that's stored. So one of your labs that you're going to do without a write-up is you're just going to create a battery from a lemon using household items. And I've just posted that to Teams, and it's due on the 1st, and that is the last day of class. You can go ahead and do it before then. So for batteries, charge carriers go from high electric potential to low, just like I just said. And the energy is converted into first kinetic energy. The more kinetic energy, the more movement, and then you have more circulation throughout the elements. So the more movement you have, the more collisions you're going to have. The collisions are going to cause heat, and then that circulates back to the circuit. So batteries store energy from chemical. You have chemical reactions that go on. Kinetic energy is then formed through chemical reactions, and then you finally have heat energy. So sometimes you can feel that in items that you have at home that use batteries. Sometimes there's some heat, especially like if you see my laptop right here, my laptop is now generating heat, and that's part of it. Although mine is plugged in, but there is a battery in there. Since batteries are finite, they are not going to allow energy to just keep flowing through. Sometimes we use generators. So when we have generators, we have mechanical energy that goes into electric energy. Now, hydroelectric power is a little bit different. They use water from falls, which is basically kinetic energy, and then that changes into electrical potential energy. So when we're at home, we are using actually generators. That's the source of our energy. So our outlets are basically from the electric company, but they are generators, and they have a potential difference of 120 volts, okay? So you know that because you've seen everything. If you travel over to Europe, it's 220, I believe, and you actually have to change and do some conversions, okay? Now there's two types of currents. The first one is DC, the direct current, and if you can see from my graph in current in amps over time, it is a straight line. It is direct, as it says, okay? So the charges in a direct current, there's two of them, two types of currents. The first one is direct, and the charges move only in one direction. Now these are negative charges, and again, this time they move from lower to higher electric potential. So here you have a battery, and a battery has a positive or negative. It has a potential difference, and you have a charge going from one wiring to the next wiring, so positive going to a negative, but this time it's going to be a conventional current that's going from positive to the terminal and then negative. The electrons are going to move in the opposite direction. So a light bulb attached to a battery would be an example of a direct current. However, everything that's plugged into our house is what's called an alternating current, or AC. So the graph for AC is obviously alternating in current over time, and you can see this undulation here, or oscillation is the better word for it. The terminals for the source of the potential energy are constantly changing signs, positive and negative. So there's no net motion of charge carriers. They vibrate back and forth. If the vibrations slow down long enough, you're going to see flickering. Sometimes you see the light flickering. Sometimes you see appliances flickering. So in the USA, oscillations are 60 times per second, which is basically a frequency of 60 hertz, okay? So electric companies are the ones that supply power in AC. Batteries are the ones that do it in DC. So sometimes you have AC/DC, like the laptop here that has power to a battery source that can recharge a battery, but it does have a battery, and that battery is finite inside the laptop too. Sometimes you may see it slow down because of that. Okay, so energy transfers from page 607. Whenever batteries maintain electric currents in conductors, your chemical energy will continuously change to electrical energy of charge carriers and then change to internal energy. So like if you can see in this light bulb, you have chemical energy here that goes into electrical energy, and then the internal energy will light up that light bulb. And actually that's usually due to collisions, and it's usually heat. There is a figure in your book, which is figure 4.3, and it talks about that and it shows the graph, and that's on page 607. So remember that electric power is the rate of conversion of electric energy, but that's not the most important. The other thing about that is that the rate of change, that it's basically the work that the carriers do, or the rate of change of work that the carriers do. So having said that, power is going to be watts over a change of time, and watts, work over change of time, and that is the change of potential energy over delta T, change in time. And since delta V is equal to delta P over Q, then delta PE, potential energy, equals Q times the change in V, which goes to P is equal to change in potential energy over time. And then you can go in, and the book goes through all of this, remembering that current is the rate of change of movement, Q over delta T. You can then take all of this and plug it into here, so you get Q equals delta V over T, or you can get P, power, is equal to I times delta T, and the SI unit is watts, or a big W. So if you kind of got lost in all that from my notes, there is a good explanation in the book about this. So it's on page 608, and you can kind of follow along. There's also the PowerPoint that I can reattach if you need to. It's earlier on in one of the other assignments. Now the last thing we want to talk about is how do we calculate this, okay? So one of the things I said is note that delta V is IR, and this is for ohmic resistors. Remember, we're assuming that everything in this book is ohmic. So since power is equal to I delta V, then I is equal to delta V equals IR. So that becomes I squared over R. So you're going to go to power is equal to I squared over R. And remember, power is in watts, okay? So electrical energy is going to change into internal energy in resistance material, or Joule heating. This is called Joule heating, or I squared R loss. Now let's look at the example problem on in this chapter, and it is electric power. So if you go through that, it gives you the problem. In 1994, a group of students at Lawrence Technical University in Southfield, Michigan, built a car that combines conventional diesel engine and electrical direct current motor. So basically this is going to a DC power. The power delivered by the motor is 32 kilowatts, so you're going to have to change that to watts since that's not SI unit. If the resistor of the car's circuitry is 8 ohms, find the current drawn by the motor. So they have given us P is 32 kilowatts, which is 3.2 times 10 to the power 4 watts. The resistance is 8.0 ohms, and our unknown is I. Because power and resistance are known, the second form of the equation is going to solve for I. So P is equal to I squared R. So I is the square root of P over R. And then you just plug it in, and then you get it. So what I'm going to do is go over number 2 with you. Number 2 in your book on page 609 is the only one I'm not assigning. You're going to do on page 609 numbers 1, 3, 4, and 5. Pretty easy again, it's just a little bit different. So the question on page 609, number 2, is a small electronic device is rated at 0.25 watts. So that's going to be our P. When connected to 120 volts, which is our normal voltage for AC coming out of our plugs, is going to be delta V 120. What is the resistance of the device? So I know that P is 0.25 watts, V is 120. volts and R is something ohms. I don't know. So I'm going to use P is equal to delta V squared over R. So see page 608 if you don't know how I got this. R then can be substituted, moved all around, and then you get delta V squared over P. So now I'm going to take the 120 volts and I'm going to square it and I'm going to divide it by 0.25 watts. And then I should get my resistance, which is 5.8 times 10 to the power 4 ohms. So your assignment is to do 1, 3, 4, 5 on page 609. Again, if you need help, if you need me, you can either contact me on Teams. We can set up a Zoom. I can do a little session with you if you need help. But just know that this is the last section in this unit, and then you're going to take a quiz, which I already posted. Well, I haven't posted it yet. You're going to take a quiz and that I'm going to post shortly, and then you have a lab, and then you have an open book test, and these are due May 1st. If you have any questions, please feel free to contact me. I know I talked with Mike already. Wyatt, I did send you a message about when you're available to video chat, but I don't think you've answered me yet. So if you can answer me, that would be great. All right, I miss you guys. I'm praying for you. I will talk to you later.